So we can start now.
Is it go live?
No, streaming already.
Let me check, please. Give me a minute. All right, guys, let's get started. So this is the 5th week of the webinar, International Webinar Series on Advancing Remote Sensing Application for Ocean Sustainability. And this came to the last week. So we switched moderator to a new one. Let me introduce our moderator for today. Moderator here is Dr. Wirod. He is an faculty member at the School of Marine Technology, Burapha University. His expertise includes GIS and remote sensing, and others Internet of Things in geospatial analysis. So I will pass the floor to Dr. Wirod.
Yes, thank you, Dr. Thachanat. So welcome to the last of this year webinar. So IOC-WESTPAC International Webinar Series on Advanced Remote Sensing Application for Ocean Sustainability. So today we have 3 presenters from 2 organizations. So the first one, we have Dr. Eligio de Ramos, right? Your name, from Northwest Pacific Region Environmental Cooperation Center, Japan. So he will present us on application of satellite-derived chlorophyll egg eutrophication assessment. Your time, please, Dr. Eligio.
Yes. Oh, thank you, Dr. Wirod. Can you hear properly my voice?
Yes, correctly.
Okay, thank you.
Let's
So
share
I will share my screen. So can you see my screen?
Yes.
Yeah, I put my slide now. Thank you for the opportunity to introduce my work. I'm Eligio Maure, and I'm working on coastal eutrophication at NPAC. NPAC stands for Northwest Pacific Region Environmental Cooperation Center. So today I will be talking about the application of satellite-derived chlorophyll A to coastal eutrophication assessment. So I will introduce an app called Global Eutrophication Watch on Google Earth Engine. So NPAC is a host body of NAUPAP-CIRAC. NAUPAP-CIRAC is regional activity center, one of regional activity center of NAUPAP, Northwest Pacific Action Plan. So NAUPAP is UNEP's, one of the UNEP's regional SEAS program. And it was created in 1998, adopted by China, Japan, Korea, and Russia. So NAUPAP-CIRAC is in Japan, Toyama here, and is one of the 4 regional activity centers. And NAUPAP-CIRAC has been working on SDG 14.1.1a, index of coastal eutrophication, using satellite remote sensing data. And our discussion today will be focused on this specifically. And NAUPAP-CIRAC has several remote sensing related activities for marine environmental watch. So here I just list a few of them, maybe some of the major. And starting from top, here we have Marine Environmental Watch. which is a website dedicated for the dissemination of satellite data, which include sea surface chlorophyll A and sea surface temperature. So this you can analyze, you can obtain data from this website, as well as do some visual analysis on the web from the NOPAP CIRAC. Also include newly developed webinar site, which will be dedicated for training on the cloud, how to analyze and visualize remote sensing data. So this is also a cloud-based tool. And we also have a tool that we developed for the validation of satellite remote sensing data, which include chlorophyll, RRS, and others. And finally, more like assessment tools that support environmental protection. Here we have the Global Eutrophication Watch. I will be focusing on this specifically today. And later on, my colleague, Dr. Genki Teraoshi, will be talking about the seagrass mapper, which is used for mapping seagrass in the coastal region. And NOPAP has been working on coastal eutrophication for over a decade, and it developed a procedure called the common procedures. So this procedure evolved over time, and at some point, it became clear that this procedure needed to be split into two, where you have a comprehensive procedure, which does as the name suggests, a comprehensive study of eutrophication, and then we have the screening procedure. So the screening procedure is intended to be used as the with minimum parameter of assessment. So this decreases considerably the amount of work that sometimes is not necessary, as I will explain later in details. So the screening procedure is used to detect symptoms of eutrophication. And once those symptoms of eutrophication are identified, so then we can apply the comprehensive procedure, which means we focus our attention where it is necessary without wasting so much resource on other unnecessary things. And this comprehensive procedure then will have other follow-up studies that will after defining the objective of assessment, the area of assessment, and other relevant information, there will be a study to analyze those parameters and so on and so on. But on the other hand, which will be the focus of today, we have the screening procedure. The screening procedure uses a minimum of parameters. And this screening procedure has been called the NOPAP eutrophication assessment tool. So it only uses satellite-derived chlorophyll A to identify areas with potential for eutrophication. It has been used in regional assessment study in the NOPAP region to identify areas as potentially eutrophic or oligotrophic, and also recently has been applied for the global scale. Here on the global scale, we call this assessment as coastal eutrophication potential, because it's only is not a definite. Once the areas identify as eutrophic potential, then we need to follow up with a comprehensive study. So we will be discussing about the global eutrophication watch today. And the global eutrophication watch is a cloud-based assessment tool of coastal eutrophication. Here is the interface of the global eutrophication watch. And you see here an assessment map on the global scale applied using satellite-derived chlorophyll A. And we will see more details about this assessment. And it uses the NEAT, which is the NOPAP eutrophication assessment tool, and only based on satellite-derived chlorophyll A. This tool was developed as a NOPAP CIRAC contribution to SDG 14.1.1A, and it was developed in collaboration of many other institutions, including Google. And yeah, I've been repeating several times eutrophication, but what is exactly eutrophication? So there are several definitions, and yeah, there have been so many definitions changing to be more kind of correct politically or scientifically, but one thing that everyone agrees that there are a few keywords in this eutrophication. One is increase in biomass in the coastal region, and the other is that this increase is caused by nutrient input. So let me just use by nutrient input. So what happened is we have a coastal ecosystem that initially is pristine, so we have healthy ecosystem, but with human activity, often as we have the human activity here associated with industrial development and other activities, or like household waste that start putting a high concentration of nutrients. So these high concentration of nutrients trigger phytoplankton blooms. Initially might be positive to the ecosystem because increase in productivity means might mean increase in fisheries, probably, like in the upwelling region, for example, where we have rich fisheries. But if this is consistently increasing, at some point, there is a limit for any system to hold this much nutrient input. And then you start to have other issues, such as decrease in water clarity. And then since water clarity decrease, light cannot penetrate to the bottom, and submerged vegetation now start to die because it cannot get enough light, and maybe you also start to having low oxygen condition because of bacteria activity to consume the large amount of phytoplankton. You have many other issues that might follow, and then you start to have this symptoms of eutrophication caused by this nutrient input. So here, knowing about this and understanding that satellite observation provide this wide scale overview of the ocean condition, we take the satellite chlorophyll and apply as a means to rapidly identify areas that potentially are suffering from this coastal eutrophication. So that's the objective of this study. So here we take, we have a long-term data set of satellite-derived chlorophyll. We combine this satellite, and then we obtain chlorophyll time series. And once we get this chlorophyll time series, in each year we extract the maximum, which means we are focusing on the period where we have a peak. So we are picking the peak increase because we assume that there is something going on that triggers phytoplankton bloom. So we pick up this bloom, and then we observe this bloom over time. We say this bloom has been consistently increasing or consistently decreasing, or nothing is changing. So these will give us information about different conditions. As you can see here on this map, you can have areas that have no trend, means nothing is changing. And then you have areas that is consistently decreasing, shown in blue, or you can have areas that is consistently increasing. And then for the areas with consistently decreasing or increasing, we call this oligotrophication potential or eutrophication potential. These are some of the important words here. And we use the sand slope method, and this is tested on 90% significance level. For the global assessment, we use combined data of seaweed MODIS at 4 kilometer spatial resolution. And then for the regional assessment in the NAUPAP region, we use a product that we developed at NAUPAP CIRAC and is available on the website. This is distributed at 1 kilometer resolution. And recently we include the SGLI to observe much closer areas like near coastal areas, as I will demonstrate later, near shore areas. And then another thing we do is, after we obtain the oligotrophication potential or eutrophication potential, which is increasing trend and decreasing trend, we also obtain the current status rather than just looking at the long-term change. We also look at the status now, and then we just estimate the time series, like we estimate the last 3 years mean, and we get the average condition in the last 3 years. So this will give us some idea of what has been the condition over these last 3 years. Then we can separate areas as being high chlorophyll or low chlorophyll based on the current condition. And we adopt a threshold. This threshold actually, here we can have a fixed threshold, but in the app, which I will demonstrate, you can change based on your own criteria. And then once we have this high and low, we can define this high and low as oligotrophic potential, not the difference. Before was oligotrophication, means there is a process running. Here we just mean is the state. Is oligotrophic potential, meaning low, or is eutrophic potential, meaning it's high chlorophyll condition. And then if we combine previous information, which have 3 cases of decreasing, no trend, and increasing, and now with this high and low, we can get this 6 condition. You can have high, but it's telling you that the ecosystem is high now, but it has been consistently decreasing, meaning, it's improving. But on the other hand, you can have high that is consistently increasing. This is a little bit not good condition that you have to pay attention. It's been increasing and remains high, so you have to focus. That's eutrophication potential. Here also, even it's low, is telling you that over this assessment period has been consistently increasing. So which means, again, you have to pay attention to this kind of conditions. So generally, HD, LD, and high HI, LI are very important in terms of eutrophication assessment here. And using this assessment and the regional data, we do a study in the Bohai Sea. And then here you can see we have assessment in the period 98-2015. You can observe that around the coastal regions, you see high increasing means eutrophication potential. And most of the area also you see even low, but it's increasing, meaning that there is an increasing chlorophyll trend. But in a different period, when we extend this assessment, you see now is 98, 2019, you observe that those patches have been decreasing, means at some point there was a reverse in the trend of satellite-derived chlorophyll A, which now is showing signs of improvement in water quality. And if we include even recent years, we observe a reverse phenomena. So here we didn't have much of this purple color, but here we can observe that they have been increasing a lot. So it means there's been a significant improvement in the water quality, and the app is able to identify those changes over time. And this has been also corroborated by different studies. So this is a very important aspect of this. Yeah, of course, here we just say what has been going on, but maybe it's also important to have follow-up studies that can then now try to explain the mechanism. This is very important. With satellite data only, we can identify, as I explained in the introduction, we can screen out areas with eutrophication potential or without eutrophication potential. Then the mechanism should be explained by more comprehensive studies. And extending to the global scale, actually, some of the very well-known areas of eutrophication, like dead zones, here the Gulf of Mexico and Baltic Sea, those are really famous dead zones. And here on top is eutrophication assessment using the Global Eutrophication Watch. And again, red indicates high increasing. And this is from this paper, Carterson, showing different assessment in 93 and 2012. So he indicates here, red means bottom oxygen less than 2 milligrams per liter. And then black means less than 0 means no oxygen at all. And you can see the distribution of these patches, kind of distributed in areas where the Global Eutrophication Watch identify as eutrophication potential areas. So it provides really good confidence on the results. And also in the Gulf of Mexico here, you can see those are the areas of depleted oxygen, pretty much identified by the Global Eutrophication Watch. So it provides really a good means to help identify those areas. So once we get this information, we can easily pick up areas that we can take samples and do more comprehensive studies. In addition, we also have this another examples in Arabian Sea. Here we see this Gulf of Combat. So Arabian Sea overall, you see increasing chlorophyll trends, and many studies have been reporting noctilica blooms in Arabian Sea, causing severe red tides here. And some reports also suggest eutrophication potential issues around this area. So like I said at the beginning, in addition to this regional study based on 1 kilometer resolution data and the global study on 4 kilometer resolution data, we recently worked to upload newly launched SGLI derived data, which is 250 meter. So this data is only starting from 2018 until now. But this has a big value because it allows assessment in the coastal region. So we NPEC, NOPAP CIRAC, uploaded the data to Google Earth Engine and then use it for eutrophication assessment. So the important thing here is that if you look at the left here, which is based on the regional data, and you look at the right here, which is based on SGLI, you can see the spatial coverage, meaning that until where the coastline ends, you can do the assessment. Whereas in the past, you see some areas like here, you didn't have data, maybe because quality of the data was very rough and didn't allow that. But with SGLI, you can cover all this area, a really small bays and all of these things. So it's really add a big value for assessment in the very coastal region. And then here, what we are looking at on top is we have we put the same. So IOC actually can start from much earlier than 2018, 2021, start from 98 because combine several data sets. And then what we do is we put the recent 4 years of SGLI. What you see is, there is a large difference in terms of magnitude, meaning that this SGLI might be overestimating chlorophyll. But important thing is, here we are just talking about eutrophic potential. So this will tell you that this is eutrophic potential, but this one will tell you that is oligotrophic potential. But both agree that there is a decreasing trend, which means both will tell you that there is oligotrophication potential thing going on. So there is agreement in terms of trend. And even here, we see much better agreement in the Ariake in Japan. So this shows the potential of combining different data sets for doing this, the importance of combining many different satellite data sets for eutrophication assessment. And I would like to just briefly show you the app do a quick demo. So can you see the app now? Can you see this screen showing the, yeah. So this is the Global Eutrophication Watch. We have several here. You can choose different language in the NOPAP region. Unfortunately, we don't have Thai, but we have English, Japanese, and other language. Here you can select different data sets. Here I'm using the YOC blended data set. So we have MODIS Aqua, IOC-GLI as I introduced. We have combination of YOC and others. So you can select. If you have your own data set in Earth Engine, you can come here and put the data here. Then you can do the assessment. Here you can select the time. You can change the time, when to start, when to finish your assessment. And here you can choose the period for the average composite to tell you where is high, where is low. You can choose that specific period you want. And you can also change the threshold here. You think it's 1, it's 2. Yeah, by default, we use 5. And then you get this. On the right here, you can click anywhere in the map, and then this will generate the time series for you. So you can explore each individual point and see what is going on. You can also add data here and push enter. In addition to that, not just, I mean, the power of this tool is that you can also split the window. You can compare directly different period of assessment. So right now, here we are looking at 98, 2015 on the left, and we have 98, 2021 on the right. So you can see what has changed in this time interval. You see that some, those I reported earlier, the shrink of the high increasing trend. So if you do this, you can see easily this. And in addition to that, not just this assessment map, you can also pick up, just compare different periods, average chlorophyll. You can just say, okay, what is the composite, only composite condition, what has happened? And you can easily see the areas that the composite has shrink or chlorophyll become higher than the threshold. So it really provides a powerful means to do assessment. And then another thing is, yeah, like I said, you see here we can combine different data sets. You have with SGLI, you see increase around the coastal regions, of course, because here we are using trends based on YOC. You see, you still have some missing data, but if you use, if you use only SGLI, you see it's really cover entirely the coastal ecosystem. So it really adds a big value. And yeah, so this is a quick demo of the app, and coming back to my presentation. So this is a summary. I just introduced the Global Eutrophication Watch, and the benefit is that it's simple but robust, cost-effective water quality monitoring for informed decision-making. Identify waters with symptoms of coastal eutrophication only using satellite-derived chlorophyll. Areas suffering from potential nutrient pollution can be identified. So note the word potential. Helps in evaluating the impacts of measure taking to reduce the effect. So if you apply some, you are implementing measures to decrease eutrophication. So then you can use this app also to check, monitor that area, whether you are getting good results or not. But also there are limitations. It only identifies eutrophication or eutrophication potential, which may also include hubs, but you cannot tell that this area is hub or not. Yeah, can only provide context of areas with symptoms of water quality deterioration. Can only identify, again, and assumes eutrophication is manifested in increase in phytoplankton biomass. Yeah, that's all from me. Thank you.
Thank you very much, Dr. Mook, for very informative presentation. So for the audience, please keep your question for the end of presentation. That we have 3 presenters. We make sure Dr. Mo stay with us. So thank you very much for your presentation. So next, please stop your share.
Thank you very much. Yeah.
But we move to the next presenter from same organization, Dr. Kenki Teranguchi. He will present us about the seagrass mapping. Right. The time is yours, Dr. Kenki.
Hello, everyone. You hear my voice well?
Yes, well.
Okay. Okay. And my slide, okay? Looks okay?
It's okay.
Okay. Oh, thank you very much for giving me this opportunity to introduce our cloud-based application for mapping seagrass. We call it Seagrass Mapper. It's an open tool for mapping seagrass using cloud computing on Google Earth Engine. My colleague introduced regional C program and NAPAP, so I'm not giving you any details, but this is a 4 countries program, and we are working together to conserve marine environment in the Northwest Pacific region. And recently we have been working closely with IOC-WESTPAC for development of seagrass mapping applications. And today I will be introducing 2 of our cloud-based applications. One is called Seagrass Mapper, and another is called Seagrass Trainer. Okay, so this was jointly developed by NOPAP and IOC-WESTPAC. I would like to thank our colleagues in IOC-WESTPAC taking this occasion. Okay, so these 2 apps are available from our website. If you type either Seagrass Trainer or Seagrass Mapper, you will be looking at this kind of interface. Seagrass Trainer on the left is application for you to register field-based seagrass records to be used for training satellite images. And on the right, Seagrass Mapper is directly connected to Google Earth Engine, and this is an interface for mapping seagrass. So far, you need both applications to work, and you can just choose to work solely with Seagrass Mapper, but you need to know how to register information in your Google Earth Engine account. And today I will be introducing how I register my dataset in Nano Bay and how I see seagrass distribution using these applications. Okay, so Seagrass Trainer is built upon Amazon Web Service and Google Cloud Platform, and it can be used in any countries. And for input files, you can input CSV shapefile, KML, KMZ. For raster data, you can upload GeoTIFF. So this is, for example, if you want to upload your own satellite images in GeoTIFF format, Seagrass Trainer will accept your GeoTIFF input. And both applications can be able to output GeoTIFF and CSV file if you want to see the classification result, for example. And both applications are capable of run classifications for mapping, and these are the algorithms embedded in the system. And for other features, while Seagrass Trainer is non-interactive, Seagrass Mapper is interactive. And another thing that Seagrass Mapper is not capable of is that it cannot be working in China. Almost like all the Google applications are banned in China. So Seagrass Mapper cannot be operational in China. So if you're accessing from China, you need to use Seagrass Trainer. Okay. And these are the what's freely available in Seagrass Trainer and Seagrass mappers. You can access historical Landsat archive data for free of charge. And we also have ALOS data and Sentinel-2 data. If you wish to use some fine resolution commercial satellite images, such as GeoEye-1, WorldView 1, 2, 3, you can purchase these images and upload into a Seagrass mapper or Seagrass Trainer environment manually, so that you can analyze those images. Okay, so I would like to introduce how to use Seagrass Trainer now. First, you have to define your region of interest. This is my example in Nanao Bay. So I just draw the rectangular shaped polygons to define the area of my interest. Okay. And you need to save this file as aoi.zip and register through Seagrass Trainer. When you carry out mapping Seagrass operations on the cloud, you need to conduct atmospheric correction. And here is a technique to do that. Picking up deep water polygons where you see no light reflection from the bottom. And by subtracting pixel values of those dark pixels of all the pixel values in the image, you can do the atmospheric correction manually. So here because I know these areas are deep enough, so I draw these polygons for atmospheric correction. So you need to do that in your region of interest. Another thing, another type of correction is called water column corrections. Because we are looking at information on the seafloors. There's light, backscattering of the light goes through the water to the satellite sensors. So you need to remove those water column effect. And to remove those water column effect, you need to draw polygons in the area where seafloor is in a uniform. In this case, it's a sandy bottom. So because I know from this field survey, these two areas are highly likely sandy bottom. So I draw this polygon, 2 polygon lines, saying these bottoms are a sandy bottom, and there is no vegetation. And these informations are necessary to carry out water column correction. And it's nice to have a bathymetry data. In my area of interest, I had bathymetry images in GeoTIFF format, so I upload this information in our cloud environment using Seagrass Trainer. And this information can be used also for deep water area masking and water column correction as well. And at last, you need to define the area, your area of interest to calculate the area extent of each seafloor class. In this case, I draw these polygons to compute the area extent of seagrass, sandy bottom, and seaweed class. And here is an example of training data. Green here indicates dense seagrass, and yellow indicates sandy bottom, red indicates seaweed. Okay, so you need to prepare this kind of information before analysis. Okay, so now I would like to introduce my case study in Nanao Bay. using seagrass trainer, seagrass mapper. Nanao Bay is located at the center of the main island of Japan, facing the Sea of Japan. And in the middle of Noto Peninsula, there are 3 small bays. And one of the innermost bay here, we call it Western Nanao Bay. There is a large-scale seagrass habitat exists there for a long time. But there has been a problem of seagrass die-off reported by local scientists, and they claim higher sea surface temperature in summertime is causing massive seagrass die-off in this area. Here is an example of this is a chart indicates seasonal changes of sea surface temperature in 2012, 2013, 2014. As you see in this figure, sea surface temperature in 2012 was higher than 30 degrees Celsius in August and September. And they claimed there are more seagrass die-off has been recorded compared to 2013, 2014. So we also went to the field to investigate the seafloor types using underwater camera. And for very shallow water, we use standard paddle surfboard. And by visual inspections, we collected field sample data. For this underwater video camera, there are 4 channels looking at horizontal detection, and there is 1 camera looking under the bottom direction. So there are 5 channels of information that we are collecting in each point. And after we obtained those images, we initially split the seafloor seafloor information into 5 types, and then made 3 classes for classifications. Initially, I tried with 5 classes. It works well for certain situations, but it's not always works better for every images. So I simplify the number of classes from 5 to 3 these days, and I use this class 1 as seagrass and class 2 as sandy muddy bottom, and the class 3 is seaweed. So to see the phenomenon of massive seagrass die-off, we went to the field in 2015, 2019. And we were able to obtain satellite images of Landsat 8 OLI and Sentinel-2 MSI. And the timing of the field sampling was done in June and October in each year. So we went to the field 4 times. And before analyzing satellite images, we conducted atmospheric correction by deep water method and water column correction by bottom reflectance index method. For classifying seafloors, we used supervised classification by random forest method, and used 70% of the field data for training of the images, and remaining 30% for validations of the obtained data. Here is how training data will look like. So the very first time we collected many samples in June 2015. And then this yellow here indicates a sandy muddy bottom, and this green here indicate dense seagrass, and red indicate seaweed. And the same thing in October, less number of samples, and 2019 June and 2019 October. And here is a classification result by giving the three types of sea floor information into satellite images, and we were able to detect a seagrass habitat in June and December, and these numbers are accuracy assessment result against the 30% of remaining training data. As you see, these green patches dominate the bay in June, but most of the seagrass are gone in December. And you see the same thing in September. But if you compare the area of the area extent of the green patches in 2015, 2019, you see there has been more seagrass disappeared in 2019. So we are curious to know if the higher sea surface temperature can be also observed in these 2 years, and we confirmed that by both field records and satellite observations, there was a higher sea surface temperature in 2019. This is public report from Ishikawa Fishery Center produced, say that sea surface temperature in 2019 has exceeded 30 degrees Celsius. On the other hand, it was below 30 degrees Celsius. It was 28 point something in 3 stations. And modest aqua SST showed also higher sea surface temperature in 2019. So we concluded that higher sea surface temperature indeed contributes to massive seagrass die-off, and so that was this interim summary. Okay. But we were also curious to know what else determines seagrass habitat in Nano Bay, because even the sea surface temperature was below 30 degrees Celsius. There has been a large-scale seagrass die-off observed in 2015 as well. And we thought, is this a physical disturbance of the water, or is that light availability in the water? And the latter can be observed by ocean color sensors. So we used ocean color images over the bay. And before using that images, we obtained this very nice seagrass images of indicating the changes in seagrass. This is starting from April and ending December. As we see in these pictures, seagrass looks very green in early spring to early summer. But after it reaches the sea surface temperature reaches the peak, there are something attached to the seagrass leaves, and some of them are gone in October and November, and then new seagrass come back in December. So these are the typical cycle of the seagrass phenology in Nano Bay, and I was curious to know the amount of phytoplankton in this bay, and then analyzed Modis Aqua images and SGLI obtain ocean color images. As you see in these two different images on the right, SGLI data is capable of monitoring detailed structures of the phytoplankton concentration. The number of pixels are significantly higher than the Modis Aqua. So we used this SGLI data and obtained time series information over the 3 small bays. And what you see in the orange is the western Nanao Bay is located at the innermost area of this Nanao Bay. The chlorophyll is the highest, and the South Bay is the second highest, and then this North Bay is more like open water types. And as you see in these figures, chlorophyll increased toward the end of the year, except this 2020. And this is corresponding to the increase in turbidity in the water, and concluded there may be a light attenuation influence on the seagrass phenology. So we concluded that while sea surface temperature in summertime contributes to seagrass, massive seagrass die-off in the Nanao Bay, also light attenuation increased by the phytoplankton increase in the bay contributes to a massive seagrass die-off in the bay. Yeah, thank you very much. That's the end of my talk.
Thank you very much, Dr. Theranguchi, to very interesting presentation, especially Thai officer. I think they look for this, and also the audience. Please keep your question for the last presentation. Yes, thank you very much, Doctor. Please stop your sharing. So next, we move to the next one, the important people that actually he carry on this webinar for 5th week already. Then today he become to presenter Dr. Pat Dr. Natasha Tachanat, what's his surname? Patharas Sathaporn from our member faculty. He will give us about the back door, right, of remote sensing. Yes, please, Doctor.
Do you hear me okay?
Yes, very good.
All right, guys. I'm glad that I bring myself to the last speaker of this webinar series. So I will present about current limitation and challenges for like remote sensing, satellite remote sensing in this region. And first of all, I would like to introduce you guys about GOOSE and GCOS, which is separate into it is operated under IOC and WMO. So here's my talk outlines. So I will introduce about satellite observation as part of the GOOSE, or Global Ocean Observing System, and Global Climate Observing System. And then we will move on to touch some variable in what we call essential ocean climate variables. And then we will demonstrate some limitation using SST and air-sea flux estimate, and then mention some points about limitation and challenges for further improvement towards 2030 strategy under IOC Ocean Decades. Of course, since we entered the Ocean Decades since last year, and people mentioned that GOOSE is kind of integral part or the central heart of the ocean decades. So WEST aim to deliver some information and service to three main areas: ocean health, climate, and operational service, to better serve people livelihood and better serve societal needs and better conserve ocean for next generations. And next, we also have GCOS, or what we call Global Climate Observing System. This is a broader range of variables, including surface atmosphere and upper air atmosphere as well. And also this variable also cover biosphere and hydrosphere. So WEST may be a subset of GCOS as we focus only the ocean and biogeochemical in the ocean. So we have GOOS and GCOS operated under or adopted under IOC and WMO. And before we jump into the satellite observation, so I would like to introduce what we have about in situ observation. This is a part of Western Pacific that show some observation system under Global Ocean Observing System of WEST. Here what we have, like people knows ARCO float, and now we have deep ARCO and biogeochemical ARCO as well. And we have many others, ship observation and repeated transect by ghost ship. And we have time series by ocean science, as well as HF radar and tsunami buoy. But we still have limitation and need further improvement in terms of some observation here. I want to point out that some observations do need further improvement to better serve or better serve the delivery area under GOOS system. First of course, HF radar, it's still not fully implemented and need more improvement in terms of data management and archive. And we have some other observation to merge between coastal shelf sea and open ocean, like ocean gliders. We still need more kind of operational oceanography to monitor our oceans. So of course, we're gonna jump into satellite observation, and here are what we have right now. We have many other countries operate many other satellites here. Let me zoom in. Of course, we have Sentinel families under ESA or European Commissions, and we have many satellite and sensor under NOAA and NASA as well. In our region, Indo-Pacific, we have leading countries like China, Japan, and Korea try to operate and launch more satellite and sensor to better serve data service. Let me jump into one variable that's the most common, and we might think it's pretty easy, which is the SST or sea surface temperature. People in ocean color, ocean remote sensing and other remote sensing might know that we have two method or two sensor to observe the sea surface temperature. The first one is thermal infrared, which gives better or higher accuracy and better resolution about 4 kilometers, but it's affected by cloud and aerosols. And we use this for like a coral bleaching alert using sensor like AVHRR. And then we have another spectral, which is a passive microwave remote sensing. They give like coarser resolution, but it can observe under cloud cover, but the case is it obscured by rain and sea surface roughness. So in reality, we try to merge these two, thermal infrared and passive microwave, to better observe sea surface temperature. And here we showed figure in the right panel that we have different perspective in terms of the SST. The one we mentioned first is thermal infrared. We observe at the skin surface, but from passive microwave, it's observed like more than one meter. So there's large variation in terms of diurnal heating and evaporative cooling at the upper 1 meter at the surface. So it might be larger than 2 degrees at the surface. This is what ocean remote sensing practitioner knows. And I want to demonstrate this. What was the problem? So the first panel or the top panel is the thermal infrared. It's obscured by cloud, as we see from the map, that the cloud cover might cause some problem around the Indo-Pacific region, but we get a better accuracy from the scatter plot at the left panel. For the lower panel, this is a passive microwave, so it's better cover the area as it can observe under the cloud cover, but we lose some accuracy. We can see from the scatter plot at the left side that there's a large variation in terms of systematic bias. And another problem for passive microwave is the land boundary. We see that between the land and the sea boundary, there's a data gap between these two, these passive microwave. So in fact, we gotta have both thermal infrared and passive microwave to fulfill the gap to better serve the data service. And as I mentioned, SST is not that easy. So variation in SST is governed by heat balance. So the first term is acid fluxes, and partial capital T is the sea surface temperature. So this is a time evolution of the sea surface temperature. It's governed by acid fluxes and many other ocean processes like lateral advection and vertical mixing. So one thing I want to pinpoint is the acid fluxes. Here the term of the net acid fluxes or QNet, it's comprised of 4 terms. Many people might already know this, but let me pinpoint. The first 2 terms is radiative fluxes. This might what you know about the short wave and long wave radiation. So these 2 are radiative fluxes. The latter 2 terms are turbulent fluxes. These are sensible heat and latent heats. So it's driven by storminess. But the first term is driven by, the first 2 terms are driven by cloudiness. So this is what, like, I try to present that these 4 terms of surface heat fluxes are the main factor to drive many others, ocean and climate variability. And let me show you about this. And this is a net surface acid heat flux. And the first, the latter 2 terms from previous slide are sensible heat flux and latent heat flux. So in order to determine these 2 turbulent fluxes of heat, we need winds, we need AC temperature gradient, and we also need AC moisture gradient in latent heat flux. So these 2 terms are the driving force of ocean and climate variability across many time scale. So as we see from this figure, that exchange of turbulent heat flux can drive a cloud transport of heat and moisture into the upper atmosphere. And this is what we still cannot measure it accurately by remote sensing. Why these 2 terms are important? Because net surface heat flux are like a driving force for many processes across time scale. As we see from this figure, we have spatial time scale in x-axis and temporal time scale in y-axis. So many processes we see in daily life or longer are mainly driven by surface heat flux here. If we cannot measure it accurately, so that means we cannot forecast it precisely as well. So here I show that the first upper left panel, this is the QNet or the net surface heat flux. We use CERES. This is CERES, NASA CERES data set. These are radiative flux combined with the OF flux. These products are like turbulent flux. So we combine radiative flux together with turbulent heat flux to obtain the net surface flux. And we see that many areas in the western boundary current, like Kuroshio or Gulf Stream, they are different in terms of the net heat gain or loss. The blue color show like this is negative upward. So that means during the area of western boundary current like Kuroshio and Gulf Stream, the heat released into the air. And another panel show the standard deviation of annual mean of the product. We see that from the upper right panel. So mostly we have large variation in terms of ocean heat flux in the tropic area. This is because of like variation in cloud cover and winds. And if we separate into 2 terms, the lower right panel is turbulent flux. We still see some large variation in like western boundary current, and the lower left panel show radiative flux. So we see large variation in this Indo-Pacific region as well. So these 2 terms, these 2 terms, radiative flux and turbulent flux, are the main problem to retrieve, to better forecast. And this is like a zoom into the region. We show that in Western boundary current, we have heat loss. This is negative upward. So many other areas like Eastern Pacific, we have heat gain due to the upwelling region. And what I would like to present today is the newly launched NASA project called Butterfly. This project gonna review the ocean impact on weather and climate by retrieve these two heat fluxes at higher resolution. As we see from these figures, if we have higher resolution of heat flux, we can better predict flux and transport across the sea as sea surface. And we can better forecast precipitation and also the whole global water cycle as well. Because the heat flux, acid heat flux also determine the evaporation and the transport and exchange of moistures. So the case is present flux products still have like large uncertainty. We show in the lower panel in the right hand. So mostly we use like the OA flux, or OA flux is from Woods Hole, and we have Alfremer from France, Hobbs from Germany, and these flux products still have like large uncertainty, more than 20%. But Butterfly project, which is newly launched here this year, gonna better retrieve turbulent heat flux at lower uncertainty, like a less than 15%. So the upper figure show that if we have the higher resolution, we can retrieve many small scale or sub-mesoscale processes of the ocean, and we can better predict or forecast using operational system. And this project, which is newly launched by NASA, also, my past PI also one of the team. So I would like to pinpoint that in the flux product, as we see from previous slide, it's involved with many variables like acid temperature gradient, acid moisture gradient, and winds as well, winds direction and winds speed. So towards the 2030 strategy, so we plan this project plan to better retrieve the all variable involving with turbulent heat flux, such as bow SST, skin SST. And also we can see from this figure that the most inadequate variable are air temperature and humidity. We still need more improvement to further retrieve these data, and also skin surface current as well. Back to mostly variable observed by satellite, we still need some improvement in terms of SST, sea surface temperature, or and sea surface salinity as well. In the only variable that we can observe adequately is sea level altimetry. So the others still need further improvement in terms of spatial resolution and temporal coverage as well. So back to in situ measurement. So if we can merge satellite observation at higher resolution, we can fulfill the gap between area coverage and temporal coverage that in situ network still lack of. So this brings me to like a concluding remark that turbulent. So this talk, I would like to demonstrate that turbulent heat flux, turbulent acid fluxes of momentum, heat, moisture, determine the ocean and climate variability across spatial and temporal time scale. So we still need further improvement to better estimate turbulent flux at higher resolution to better serve societal needs and scientific needs towards like the good strategy at the end of the decades. And Butterfly is the newly launched by NASA, designed to retrieve all data needed to estimate the sensible and latent heat fluxes at higher resolution, less than 25 kilometers, and better uncertainty, less than 15%, to meet the scientific requirement. So that's all, and I will stop.
Thank you very much, Dr. Tachanat. Let's give us the very progress of physical and climate information. So we need to wait Butterfly, right? So then we we move to a session question and answer. So we have 3 presentations. So maybe the audience need to specific the one who answer you the question. We have application of chlorophyll A assessment, Dr. Eligio, and we have seagrass mapping from Dr. Kinki, and also the last one, the climate and physical property from Dr. Tachanat. The floor, please. Any question? I did not see any hand. Oh, please, Endo, please.
Yeah, thank you very much. I have a question to Eligio. So you show the regional analysis at 1 kilometers in NAUPAP region. So could you please tell me where is the NAUPAP regions? And one more comment is, do you have plan to extend the 1 kilometer resolution to the Southeastern Asian region? That is my question. Thank you.
Yes, thank you very much for the questions. The NAUPAP region, or maybe it's the sea around Japan, China, Korea, and Russia. So maybe I can just briefly show you exactly where it is, if it's okay.
Yes, please.
So yeah, so here, showing in this red box here, so it's mostly around this area. Of course, we extend a little bit west, including Bohai Sea, but most of the data is limited to this geographical scope, so it doesn't go beyond that. And the product we currently generate is only around this area. Of course, with collaboration with other interested partners, it's possible to extend to other regions. That's for sure.
Yeah, so thank you, Eligio. This is Ken again. So 4 kilometers analysis you are providing to the global scale. So
yes.
So that data set should include the Southeastern Asian regions, right?
Yes.
Okay, thank you very much. Just want to confirm. Thank you.
Yeah, thank you.
Yes, thank you. I saw from message box, Dr. Kinki give us the website of seagrass mapping, right? So you can get that. And another question, can audience and give the copy of presentation? Maybe after the webinar finish, then we try to summarize and give you some presentation if the presenter allow us. So I not see any question, any hand from audience, please. Okay, no. Dr. Somkiat, please.
I just would like to follow the can question, can handle question. Yeah, as you mentioned, that is your product cover the Southeast Asia. It means that on your website that when we select the area to look for that kind of result, it's already Southeast Asia already, the area is already in your website that you show us, or we have to process the data by ourselves.
Yeah, thank you again for the question. The application by default, when you open it, it gives you global data set. So you can zoom in to any area in the world. But this data set is only 4-kilometer resolution. So there might be limitation if you want to look near coastal regions where the issue often happens. So in the case of NAPOP region, we just produced our own data set with better resolution, which is 1 kilometer. So to answer your question is you might need to have your own regional data set for better assessment results.
Yeah. Okay, I understand. This means that if we need to do this similar what you are showing, we have to do the process, the data by ourselves. You think the satellite data set is already available on the internet, right? Yes. Okay. Thank you very much. And then I could have the second question to the second speaker,
please.
Yeah. It's we quite interested, in the Southeast Asia, particular from the WESTPAC community in do the C-class mapping, because we would like to move to the operation. It's not just do the research. Do the research. We know that it takes time to collect a lot of data in the field and finally when we go to the operation, sometimes we face some difficult. I would like to add that Kenki, that in terms of your study, I try to understand, what is your study. In your study, normally the C-class in your study, what is the water depth, of your C-class you do in your study, because we are thinking about how it's the same or different from Japan, and then we are thinking about how to improve our study as well. That is my first question. Yeah. I go to the second speaker. Yeah.
Okay. Thank you very much for your interest in my study. In case of Nanao Bay, the field that I just presented as a case study, seagrass often lives until 4 meter or 5 meter at the sea. And that's the very usual limit. And this bay, in this bay, seagrass habitat in very shallow water. And usually the water is not that clear. So if you go like deeper than that, you don't see much seagrass.
Yeah.
On the other hand, if you go to another site of we call it Toyama Bay, situations are different. Water transparency is a lot higher than Nanao Bay, and the seagrass then lives even like 20 meter surface depth. So the one I just presented is a typical seagrass habitat in shallow water, but there are other types of seagrass habitat in our region too.
Yeah, okay. Thank you very much. And I have the second question for you as well. Normally when you do this kind, of the study, because I'm thinking about operation as well, normally you need those kind, the field data, right? To train or validate your study. Normally, how many, for example, it's an area of your study. Is normally how many data point you need for validation or train your analysis in your analysis? Yeah.
So these days in Nanao Bay, which in Western Nanao Bay is about 6 kilometer width and 6 kilometers, let's say 6 kilometer in the horizontal direction, 6 kilometers in the vertical direction. And then we set up more than 100 fixed stations. And we collect those samples within 2-3 days. So, so that's the scale that I'm talking. And yeah, does it answer your question?
Yeah, thank you. Because I'm thinking about in terms of, because if we think about the operation, for example, to do the study, the mapping of the C-class, for the country, if it's to do those kind of data collecting for many days, I think maybe that is some kind, maybe some of you call the barrier for to do those kind of operations at the country level for the particular area. I think it could be possible. That's it. Thank you very much for your sharing the data. If you don't mind, could I ask you the last question? Because when you study in the shallow water, and you mentioned that you are trying to do the atmospheric collection to find some place that no reflection from the bottom of the sea, right? Normally, I thought that it should be supposed to be quite a deep water. Is correct? You have to shoot the deep water. Yeah, it can be anyway. It can be anyways. It's at any point. It's even outside the C-class area. Is it? It can be used that one. Maybe because I'm thinking if it's far away from the site, we are going to do those kind of mapping. Select that the depth deep water is outside the area of our study. It's okay to use that.
I tried that before, and it works. I mean, you can choose very deep water polygons outside of your region of interest, but I think in normal case, it's better to pick deep area in your region of analysis. I mean, in your region of interest. That's what I recommend. But if your region is all shallow and there is no such deep water spot, I think you can pick the polygons outside your region of interest.
Yeah. Okay. Thank you very much to learn from you, because you are expert. You're working on this field for a long time, and as you mentioned, you tried before, because it's good for us as well. Because Dr. Willow, the moderator, we have been working. We are quite new in our group. To work on this one. It's good to learn from you. Yeah. Thank you very much.
Also, I have a question also on the C-class mapping for Dr. Kinki. So how you deal with the water, turbid water? The turbid.
There is not much you can do to select better quality image. That's one thing for sure. And another thing is we have two types of water column correction selection. One is bottom reflectance index. This is using bathymetry data for correction, for water column correction. And we know bottom reflectance index method is better in turbid water than the other water column correction method, which is depth invariant index. It's independent to bathymetry data.
Okay, thank you very much for your answer. And another question for Dr. Eligio. So the application that you show us, eutrophication, was we need have to like a Google Earth Engine account or not?
Oh, you don't need any fee. You don't need any account. You can just run as a regular.
So anyone
URL.
can use that.
Yes.
All right. Thank you very much. And another question. I have the last question for Dr. Tachana. When the butterfly with our we can use for the butterfly data available, maybe the schedule.
It's gonna be launched like next month, next year, and then last for like this is like a pre the test. It will last just for 2 years first.
Okay, so we wait for that. Any question from Paul, please? Now I not see any hand. So otherwise, if anyone, no, I will stop this session and thank you very much.
Before that.
Another one. Yes, please.
Yes. Before that, this one is maybe it's not the question to directly to only the speaker. I would like to ask to share, the what you call the way of thinking, to use the remote sensing for ocean study. That one is we know that we are present today. We are using remote sensing for the habitat mapping, or even used for the eutrophication. But I also would like to hear from the speaker and other people as well. What do you, for doing the last 5 webinar, what do you think about what is the application we really need, for our region as this particular now? That's it to help us to solve that kind of, the country need. I know that it's because of eutrophication. I know that it's the one is very important, particularly if we can use eutrophication and then use the projection, particularly if we can able to do the model to projection and to do the kind of prediction also. It's very important for the country because the country would like to know about that in terms of they can to prepare the readiness to face that kind of problem in the coastal water. And from the sea class mapping is one of example of the resources. The mapping is for the what you call for the country or for the government to plan for the management that kind of habitat, because the sea class, I know that particularly in the tropical, not only in Japan, in the tropical also very important because it's one of the nursery ground of many marine organisms and also important to the local people as well. I would like to hear from the speaker or other, our participant, what do you think is other, issue, related to remote sensing, or what the remote sensing we can use for particular issue that we are really need now for the region. Yeah, that is just for I just would like to throw this kind of question to everyone. Yeah.
Everyone can. Anyone?
Yeah, it's your contribution, also can help us to think about the future, what we should move, to serve, to help, to support the country. Even you also can join with us, your effort can join your effort with us to do something for the country in the region and for the government, for the people in the region. Yeah.
So I see the hand. Please, Dr. Mr. Wang.
Yeah. Thank you, dear Songkat and all. And actually, I'm a Hamburg Bloom study researcher. In my areas, I'm also trying to do some application using the remote sensing. I just want to share some experience on this part. As we know, the Hamburg blooms it's just like it's not happened can be predicted as our current technology as current technology. We using the no matter how the traumatic like the microscope observing, and also even nowadays we're using some molecular work. Though it can be a little fast, not that we not need that much of human resources to using the microscope to identification and so on. But even this kind of technique is also have their limitations, as we just can see the harmful algal blooms on site, or it's the sampling site, not the big areas can be detecting. So for some further fast detecting or rapid detection technology, we thinking to using remote sensing, especially basing on the chlorophyll as an indicator. We are trying to also, my group is trying to using the remote sensing data and especially on the chlorophyll to indicate the harmful algal blooms in some specific region, but it needs a validation later. It's my thinking and my experience on the remote sensing using on the harmful algal bloom study area. Thank you very much.
Yes, thank you very much. For algal bloom also, some area is very very important in the topic. Any sharing?
Could I share with maybe just I asked Peng Bin maybe this big question, because in terms of remote sensing that or other people also can respond to this question. It's in terms of, I know we know that algal bloom is very important. If we can predict or know in advance or even a week or few days, it also can help, the local government work with the local fishermen in terms of prevention of some kind of impact from the algal bloom to the fishery. But I don't know that in terms of the sensitivity of remote sensing, in terms we have high resolution. I don't know that it's how the level of the concentration of chlorophyll it can detect. Is that the code question? Maybe I think is the first speaker can respond to that. And then if we can detect it, it's very sensitive to detect even low concentration. It's possible that if we can have the regular, dairy, remote sensing picture and looking on the the tendency of that kind of the increase or decrease of the plankton in the water column, that maybe is also other opportunity for us to some kind, the project is possibility of going to have algal plankton boom in the next few days or not. That's it. My question. I would like to ask Peng Bin and also the first speaker also, if you have a knowledge about the sensitivity is also if you can reply to my question, it's good, because I'm thinking about how we can benefit from remote sensing as much as possible.
Okay, thanks. I will reply first from my current experience and with my working process. Actually, for HAB, so far I'm trying to using the 50 meters satellite image for this kind of work. But just as Dr. Songkiat to referred, how the resolution and the accuracy and for HAB, which really a big questions now. So far, my process is to using the chlorophyll maybe for over 5 or 10. We can know the chlorophyll microgram per liter. We can know if there is much of the potential the harmful algal blooming is there. And there is another technical point is that for that, not all the HAB, the harmful algal bloom species, especially on some toxic species, it can reflect to the watercolor change in the water. Sometimes very low density but high toxic species is there. But for this kind of cells, it's really hard for us to detect them. And this kind of cells is oftenly can make a very huge disaster to the fisheries and aquaculture. This is the point. But we can know that if somewhere we can know there is a harmful algal bloom or there makes the disaster, we can use remote sensing data to detect or even tracking their moving directions or area. This is what we can do. We can try to make a further step using remote sensing data on harmful algal bloom. Further or 1 day or 2 days where they can go, and if they will go somewhere, we can doing something to preserve our aquaculture or fisheries. Yeah, I think, yeah, just for this, I will say this. And another point is that the current remote sensing data, there is, how can I say, because I'm not a remote sensing researcher, but we are using the remote sensing. I found that even in China, so far as I know, we didn't have how can I say, the satellite data is not supplied from every hour, but some satellite can stay in one position, can continue to give us the scenery of the watercolor pictures. For this is maybe the later also need our regional to thinking if we need a regional some just like for one position kind of the remote sensing satellites to continuously to supply some to us some kinds of the satellite image. Yeah. Thank you for this.
So we need few
yes.
money. So please elect you.
Yeah. So yeah, actually, I myself, I do not work on hubs, but from the knowledge I have, is important thing about remote sensing is that the first thing we can think about spatial and temporal resolution. In terms of spatial resolution, of course, for hubs, higher frequency will give you better information. For example, think about GOSI. GOSI will provide you information every hour. So which means that you can observe a phenomena in the same location for a sequence of time. So in that case, you might increase your power of predicting movement of certain water characteristics. And maybe if you have some algorithm that tell you about extracting information of remote sensing reflectance, relating it to hub, you can get some prediction power. The other thing is spatial resolution. Of course, higher spatial resolution definitely will give you much better information because hubs are very local phenomena. They are not kind of widespread like, yeah, in some cases you see really huge widespread harmful algal blooms, but in most cases more like patchy phenomena. In that case, you tremendously benefit from high resolution information. Think about the hub that occurred in Hokkaido last year. So with SGLI, actually, one important benefit was that researchers there could even identify the source and track it, like how it moves, and it give you this wide context. Whereas in situ information is very important, but in most cases you miss the large picture because you get sample in one point, but sometimes you don't know where this came from. But satellite can give you that chance to take this source and look back. Okay, this chlorophyll, where it came from, how it. So this is these are some of the aspects of remote sense. Another important thing is, yeah, like Dr. Wang just mentioned, hub is not always associated with high chlorophyll or low. I mean, it's not just only high chlorophyll or low chlorophyll. There are cases where you have very low chlorophyll but very toxic, like he mentioned, and sometimes even reflectance of hub is weak, that make difficult another challenge for in terms of remote sensing. But this just tells that it's very important to have some information about the local environment, then associate with satellite remote sensing. But the big benefit of satellite remote sensing is that it will quickly give you context, just like the eutrophication case. You get a better context, like what are the areas that typically this kind of phenomena happen, so that you can better plan and prepare. So remote sensing really helps in that aspect. It cannot really answer all the issues associated with what is happening on the ground, but guide you to focus more easily on the most important area and have a better look of the issues that you have to focus on.
Yes, thank you.
And also there is a issue of training also important. I mean, we know remote sensing is important and all these things, but I think there's been a gap in terms of capacity building. I think we have to invest more on capacity building, because newer generation need to have a better understanding of how to use this remote sensing, not just have data, okay, I can use it, but how to use. And in that spirit, for example, now PAP-CIRAC has been developing these webinar sites to support this capacity building, so that we can better use and have a better understanding of what is remote sensing, how we use it, and what information we have there, how do we read this kind of thing. Yeah, thank you.
So maybe we have a training session for the remote sensing. So according to the time, no, Dr. Sopket, okay.
Yeah. Could I have one more question to the Dr. Jenki? You know, because of you do the mapping of the sea class. I would like to do you have any experience, you know, working on the coral mappings, coral or coral reef mapping? Do you have any experience on that? If you have, you know, if you can share with us about, you know, how is success or what is the difficult or is possible to do, you know, the coral reef or coral mapping using the in terms of, you know, use it for the operational, because I think it's because that for the youth conventional mapping it consumes a lot of time and a lot of budget. If we can apply using remote sensing, I think it will be the other option for the country as well. Yeah, just if you have the experience, you know, can share with us. It will be good. If not, okay, it's no problem. Yeah.
To be honest, I haven't done coral
Okay.
mapping, but in principle, it's the techniques will be the same. So yeah, all you need to do is to prepare a training data set and train satellite image, the pixel values to do the classification. So yeah, please try using seagrass trainer for seagrass mapper for coral reef mapping as well.
Yeah. Okay, thank you very much.
So we can learning together. Shall we start now? So according to time limits, so I want to thank you every presenter and every audience to another contribute to share our experience. Then we can I try to stop my as possible and then give back to organizer, the main organizer, Dr. Tachanat, please. Thank you very much.
Oh, we close for the last session of the webinar series, and before leaving, shall we have like a group photo?
Yes.
Yes, could you please?
All right, 1, 2, 3. 1, 2, 3. Oh, some more. All right. Let me capture again. 1, 2, 3. Thank you.
Yeah. Before you close the session, could I have the few words to the all speaker? First of all, you know, because my colleague when Dr. Vinshichu, the head of WESTPAC office, could not join us today, I think because of other busy schedule. I would like to thank to all the speakers and also to all participants as well to join us during the last 4, including the 25 webinar. I think we learn a lot from all of you, and we are still looking forward, if possible, it's some time to ask you to join a speaker or to join us in terms of sometimes we need to learn from you as well, more about how we can develop some kind of substantial, using remote sensing for the ocean, in the for this region, Yeah, thank you very much. Yeah.
And we hope this not last webinar from IOC-WESTPAC. So maybe next time we can join again. Thank you very much.